Good afternoon, everyone. Today I will be presenting my lab work on the topic LED matrix and the keyboard interface, where I have integrated these two modules to basically print a circle moving in and out in the LED matrix by integrating these two modules and using the Intel 8085 microprocessor along with the programmable peripheral interface. And this project work demonstrated how the microprocessor communicate and interact with the input and output devices. So let's get started. This is a basic overview of the topics. So LED matrix overview and type, basically its spin diagram, then working principle and also assembly code. And in the later half of the video, we will be covering the keyboard interface, how it's integrated to the LED matrix, then its pin connections and also its assembly code, and finally some observations and some of the techniques we can do. So first part is the LED matrix interface. So LED matrix overview and types. So basically, as you can see, a LED matrix is a 2 cross 2 grid, where 2D grid of LEDs. They are arranged in rows and column, and 8 cross 8 variant where we have 64 LEDs, and they are controlled via the 26 pin FRC cable, as you can see in the image as well. So we have, as you can see in the image, we have a 8 cross 8 grid patterns of the LEDs, and there is the 26 pin FRC cable that we use to connect this to the with the 8085 microprocessor kit, and this we have the connector pins with the ground VCC and the connector pins, and the common anode is for the row pins tied to the VCC, so they will basically columns driven low to turn on the LEDs. And finally we have common cathode that is to the ground connections. So basically this completes the circuit to enable this module. Then multiplexing. So a very common thing is a that this is a 8 cross 8 grid pattern of the LEDs. So there will be 64 LEDs to control. But do we actually require 64 input output lines? Because that will be too sophisticated tool to be used. So basically to tackle this problem, we will be using multiplexing. So basically row scanning method is used, so that activates one row at a time, that cycles the fast enough persistence of so each row is scanned at a particular time. So only we will be requiring 8 scans, and in those we, as we will see in the in the coming slides, then that the hex code is being used. So basically scan each of the rows at a time, and the scanning delay is there, but that delay is not too much to overcome the persistence of vision. So because of the persistence of vision, we do not see as a pattern or as a discontinuity in the rows, or when the LEDs glow, we see it's a continuous image or it's a continuous pattern. Hmm. This is a circuit and the pin connection. So basically, LED component, what we require is a 8085 microprocessor along with 822 peripheral programming peripheral interface, and then 8 cross 8 LED matrix module, then 26 pin FRC cable. So basically, if you see the pin connections, so we have in the right hand side of the image, we can see this is the 8085 processor. Then there's a peripheral interface connected. So basically, this has two ports, port A and port B. So what we have tackled through the multiplexing technique to control the 64 LEDs is by the rows and column methods. So port A is basically for the columns, and port B correspond to the rows. So basically, port A, as you can see, from 0 to 7 lines, that is total 8 output line, and the port B that correspond to PV0 to PV7, that the row lines basically, and they are then connected to the ULN2803 to get the output on the LED matrix, that's the hardware device. So 8255 control words and the address map. So basically when we receive those data bus, so that database is then transported through this UNL 2803 finally through the 8 crosses. So and UNL 2803 is basically used to basically prevent this chips and the microprocessor from being getting damaged by any electric surge or any other external liabilities. So yeah, then we will see we have already seen, we will not go in deep into 8255. So we will see now the assembly code, how it's done. So this is a basic assembly code of the LED matrix, and that will be used to get the output of ABC. uh, Now you can see at the addresses, we will be starting from 200, and this is your operation code. But for the understanding in our language, we need the mnemonics. So basically, at the first two addresses, this is basically used to defining all the ports at 8255 as we are seeing port A and port B's. So that will be defining as the output ports, and then in the second part we will be loading the counter values for the number of characters that we need to be displayed. So first we will be loading in the accumulator, and then the output ports will be declared, and after these things we will be going in sequence to basically load the values. Then first is will be pointing to the first data at the 2006 address, then saving that value to the data pointer. After that thing, loading the counter for deciding the delay. As I told that row scanning is there, but in row scanning there is a slight delay. So that is the thing for which a character will be displayed. Store the counter for 8 values to be outputted for each character. So for a row there will be 8 values. Actually there will be there for each character. So this is the thing. And then finally in this set of programming, this will be controlling the out data for the rows. As you can see, there will be based on two things, or rows and columns. So this is for the rows, and this is out rotating zeros on the column patterns. And this part is basically used to give a delay into the codes. So this is the MOV move from accumulator A to B, and this is the move immediate that A and a value of 40. So, and this is the thing where we are using the loop and the decrement increment methods. Basically, to after getting the printed on the LED, we also need that thing to be printed in the loop manner. So, like for the LED, we are using three patterns to be displayed on the LED matrix, and they will be played in the loop. Uh, so I will come to the address location where we will be supplying the data to get displayed for the favorite pattern, whatever we want to display on the uh, LED matrix. Okay, so we will be starting from 2050 address, and this is the address, and this will be used to get the display A. Then from 2058, this will be the co- code that will be used to display B, and this is finally to get the C. Now I will get a brief about how this usually works in a microprocessor. So how this LED displaying works. So basically from the 2050 address, we have a F8, and this is for 2051 address, and so on and so forth till 2057 address. So basically what is the thing that F8 is a hex code, and this is basically broken down into two patterns, F and 8. So basically F correspond to the lower half. So this is a representation of an 8 cross 8 LED pattern grid, and basically lower half corresponds to the first by first word of this F8 and corresponds to F, and the later is corresponds to 8. So basically, and when we broke down this F into the bit pattern, it will be something like 1111, and 8 will be 1000. So basically what this sends a message or to the information to the microprocessor is that it commands the microprocessor to give the signal or glow the LEDs at the side whose bit is 1, and if else other than that is 0. The lower part of the grid, however, correspond to the first half of the X code, like this is F in this for 2050 address, and the upper half corresponds to the 8 for the same address. So this is basically how we are able to control through this data 8 LEDs at once, and this is the technique behind this. So it commands it only bottom. So if we go to the F8, so it commands it F correspond to four ones and 8 is 100. So it means that for F, 4 LEDs have a signal of 1, which means 4 LEDs from the bottom will glow. And for the 8 that goes from bottom to up, so 8 will be like here will be 1, then 0, 0, and 0. So only after that, this first line in this in the upper half will be glowing, and the 3 LEDs from here they will be 0. Similar goes in the 1 4 code as well, and 1 2 1 4 is 1 4 will break down to 1 into 0001. So just below the just below the upper column only one LED will be glowing, and corresponding to 4, which is 0100. So it will be like in the upper case from the middle, the second LED will be glowing and the remaining two LEDs will be off. And after this full conversion, we will be having something like this on our final LED. So where the black dots are there, so this is representing where the LEDs will be glowing, and the white circles are representing where they will be off. And we can easily control these things uh, if we change the data and the codes at the respective addresses. So this is only for 2050 to 2057. At the 2058 it will be starting as we see in the previous slide. If we start this, if we enter this thing, then in the second pattern it will be printing B, and in the and if we enter that code at this address 2060, it will print C, and this whole pattern after this thing will get in a loop. So A, B, C, then again when it's over, then again A, B, and C will be printed. So this is the basic thing of the, yeah. And first, I have used it. So as a part of the innovation, I have made a Trident using this LED matrix in the 8085 microprocessor. So basically, the basic code remains the same. Only I have changed is the loop pattern and thus and loop pattern of their occurrences, and also the data at the data addresses. So what I've done is the 20500F is done. So this is only changing what sequence of the LEDs I want to make it glow. So for the Trident making, I've entered this data at the respective addresses 2050, and the remaining 2058 and from the address 2060 is for the other two weapons that I have demonstrated. So below is the, so next is the video. Please do watch it, that how I demonstrated the making of the Trident using the 8 LED matrix, and then we will cover the next part of this lab work.
LED matrix is a light emitting diode matrix. So as you can see, this is a 8 cross 8 pattern grid for the LEDs, and basically we can draw a pattern in sequence of 3. As you can see, there is a light emitting diode, and we can edit the pattern based on the OP codes, and according to that the pattern will glow. So what I have built today, I have modified it to a pattern of Trident and some more weapons. Now I will display that. So yeah, you can see this is the pattern of the Trident exactly here, and this is some other weapons. And
Thank you for watching the video. Now we will be starting with the keyboard interface integrated with the LED matrix. Okay, so integrating the input output via the 8255 chip, time multiplex keyboard scanning, and the LED refreshes a single loop cycle. So LED matrix if we come, that's the 8 cross 8 grid pattern. So port A is for the driving those rows and port B is for the columns. One row is activated at a time, and at high refresh rates, persistence of vision is creates a stable and non-flickering display at the at the at the module of the LED matrix. Debouncing, so there is a time delay, but that again that time delay is too low that it is beyond the persistent vision. So we just see as a continuous image and not as a flickering or as a pattern performing one after the other rows is scanning. As part of the keyboard interface, so basically we have used a 5 cross 4 matrix, and 20 keys are addressed with 8 input output lines again, and 8085 basically drives one row low at a time, and it reads the column. Just in a similar way to LED, but there's a slight difference. A low on a column signals a key press at that row or column intersection. So basically, it's like whenever that is pressed, so it will detect that at which row and which column that key was pressed. And key detection flow. So derive row flow, then it would read the columns, and then it would try to identify the row low column as well. So, and as we are concerned with the integrand operation, so 8085 time multiplexes both tasks in a single loop cycle that alternate between the refreshing those LED matrix and then scanning those keywords at which of the pattern is being pressed. A single 8255 chip manages all input output lines, and that keeps the hardware compact and the software flow very much predictable. This is the basic keyboard interface circuit pin connections. So So basically, components we have is the 80585 microprocessor, 5 cross 4 matrix keypad interface. Then there's a pull-up resistor on the column lines. Now again, the pin connections is through the 8255. There's port A and port B. Port A again is corresponding to row lines, while the port B correspond to the column lines. So this is, you can see, port for the row lines, it is for the output that drives the low one at a time, while the column lines is for the input that read to detect which key was pressed. So this is the major application. Okay. While the pull-up register, as we will not discuss much, but as part of the work is concerned, pull-up register basically keep the column lines high when no key is pressed, and when a key is basically pressed, the signal will become low. As you can understand the working of the register as well. Also, due to the mechanical noise, we use debouncing delay to avoid the multiple false detections as well. So this is the pin diagram, and this is basically port A, and this is the port B, and this is connected through the 8255 chip. And this is the connections as well. And these are the pull-up register that are basically used to control the mechanism. And the combined system, the system works in a loop where LED displays continuously refresh while keyboard is scanned, and it allows both input and output operation so that they can occur simultaneously. This is a so yeah, that has uh, uh, explained like in the previous slide only how this keyboard is scanning and how it's working. Now we will see this assembly code. So again, as similar to the analogy to the LED, it's again initializing 8255. All the ports is being initialized. Then it send the control word, then from this calling call to 100, the scanning of the keyword get start. And again, just like in the any programming, like we have if else function similar to it. So basically it does like if that is there, do particular statement. If that is not true, the other statement will be there. So this is the thing, if that key is pressed, move on. If no key is present, then scan again. So basically it is trying to make it as easy as it could work, then selecting those pattern, after that displaying the pattern, and then repeat forever. Then keyboard scan routine after this. So there is a scan bit, then we are moving the scan pattern, sending those scan pattern to the port C, then port A will be reading those for the row lines, then mask lower bits. If that key is detected, then rotate the scan bit. And in the next part is concerned, so again this is the thing that is moving information from the accumulated register A to register C, then jump scan, continuing the scan till we get the pattern, and after that return to main. So again this is something like we see in the programming, that there is a return function, return after the end of every function to basically get output of the function that is being used. Okay, and this is the thing, and finally we have this the data table. So this is an integrant code of the keyboard scan and the LED matrix, and finally we had a data table for the LED matrix. So this is so what I am trying to display is a circle moving in and out on the LED matrix, and this is the 20 that data address again starting from 2050, and this already I have demonstrated in the first half in the LED matrix how this data on these data addresses are being able to get the information to the LED matrix. So please do watch the video, and it will like in that I briefly explain about the system working, and also demonstrated how when I will press a key at the keyboard interface, uh, there will be a display on the LED matrix.
Hello, hello everyone. Today I have made a project by using LED matrix and the keyboard interface. So basically, the LED matrix displays a circular pattern that is generated using data stored in memory. And when I press a key on the keyboard, it triggers an animation where the circle moves inward and outward. Now this effect is achieved by changing bit patterns and using the delay loops. The microprocessor continuously sends data to LED matrix through output ports that could create a smooth animation. And this project will interface demonstrate how I have integrated interface, keyboard interface, and the LED matrix input output operations. And also I have made simple real-time control using the 8085 microprocessor. So here's the complete demonstration where I've entered a command in the keyboard interface and it got displayed by the circle moving in and out.
Thank you for watching the video. So this is all about the LEDs and the keyboard interfaces. Now, basically, if we see, these are some of the interface use cases we can have in this. Like we have a caps lock indicator. So pressing the caps lock toggles, an LED goes on or off. That gives an instant visual status feedback as well. Typing mode. So insert versus override modes are reflected distinct LED color. One thing that in this experiments we have done only on the particular monochromatic light LED, not on the polychromatic or different different LEDs. So yes, we can do if we have different color, different wavelength LEDs as well. Error alert we can have, so an invalid key when pressed it flashes the LED red signaling an error without a screen pop up. While we have a shortcut to confirm, executing a keyboard shortcut lights up an LED to confirm if that action was registered or not. Idle detection as well, after the inactivity an LED dims or it changes the color to a signal low power or an idle state. Then there are security lock features we can have. A lock key combination activates an LED to basically show the device if there's in a secured mode or not. And this is finally the summary that LED matrix, it's is 8 cross 8 matrix that is driven by majorly 8255 chip having port A and port B, port A for the columns and port B for the rows. Row scanning is at 2 milliseconds per row produces. So there's a delay when scanning, but that is not sufficient to be observed by the naked eyes. And because of the process of vision, we see it's completely ordered and not in a discontinuous manner. And also we are using ULN 2803. So basically this is handle to sync current protecting the 8085. And we have keyboard interface that's a 5 cross 4 matrix grid pattern. Observations what we have observed that both interfaces use a 808255 mode 0, making the design straightforward and reusable. 8085 input and output instructions provide direct efficient code communication. Timing is very critical in them, but it should not be too fast cause if flicker on LED matrix or false reads on the keyboard as well. Both circuits they can be combined into single 825 port using port C for any additional control signals. So yes, that's all for this part of the experiment using the Intel 8085 microprocessor. And thank you very much for the for watching this video. I hope in the future